very much, everybody, for joining. Welcome to another Black Hills Information Security Active Countermeasures webcast. This one is really awesome. We have Paul Clark on. I've known Paul's brother for a long time, and his brother always said that Paul was much cooler than him. And I met Paul, and that was true, and that was fantastic to meet. I'm just giving Dave as many.
It's a low bar.
So much. He might actually be on listening, which would be just perfect. But no, SDR is one of those areas. If you noticed, about 2 years ago, I started talking about it more on webcasts, and we started some hands-on labs for Wild West Hacking Fest, and that really came from Paul and David's work. The name of the book is Field Expedient Software Defined Radio. And are we up to 3 volumes now, Paul, or is it still just the 2?
We are up to 3. Oh man, I got David's book.
There you go. The Field Expedient Linux.
There we go.
It's awesome. And all, like, black magic always seems to permeate in software defined radio, and you just see people do stuff and they're like, how did this happen? And they never share the magic under the hood. And Paul and David do, and they give a tremendous back into the community. If you go to the Field Expedient software defined radio website, there are tons of downloads and examples and all kinds of cool things.
Fieldxp.com.
What is it? Fieldxp.com?
Fieldxp.com.
Fieldxp.com. So go check that out. Go to the download section. If you're like, what is this for? Go get the book. The book is awesome. So I am going to hand it over to Paul.
So you might have seen a big, long 10-word name for the presentation. I shortened it to this little 4 thing. Squirrely Exfil with SDR. You'll see why the squirrels are involved in a little bit. And just a brief note or two about me. I'm a engineer, as you can see from the picture, and I haven't updated this slide in a while. It's been about 5 or 6 years now that I've been doing SDR related InfoSec. Before that, I was a chip designer, did mixed signal microcontrollers, and then spent some time doing some software development tools. So I kind of been all over the map in terms of engineering. And just a few years ago, I decided that I wanted to focus a lot more on software defined radio. And so I started up a small outfit that focuses on RF related InfoSec solutions, tools, books, and training. So that was one thing John mentioned. I'll be teaching again at the Hackin' Fest in October of this year. So there'll be an intro SDR course then, and I'll also be at Black Hat this year doing my introductory course as well as an intermediate course for anyone interested in that. The other interesting stuff that came out of the project you're about to see is that I ended up building another course. Got a reverse engineering course as well, but I ended up building a 4th course. These are all 2-day long, but this last one is focused specifically on building radio applications with GNU Radio, the GNU Radio API, as well as Python, which I know lots of times you'll see RF SDR solutions out there that use a lot of C++. There are times where that's necessary, but what I've really come to believe very strongly is that the overwhelming majority of stuff that most people need to do, even if it's fairly complex, can be solved with a little bit of Python and the open source GNU Radio API. So let's get into that a little bit. What are we here for? So from going to give you a kind of a 10,000-foot overview of the problem that I gave myself to solve, and then dive a little bit lower into the system overview, just kind of the hardware and software that I use to solve the problem, and then the live demo, which of course, given that we are dealing with both RF as well as fun software issues, keep our fingers crossed for that, but it's been stable every time I've tried it so far, so what could go wrong? The 4th bullet point, I think, is almost the most useful one, which is the sort of the useful things that I learned along the way. And there's a lot of stuff in GNU Radio that has great examples and great walkthroughs that you can follow along, understand. I would say that when it comes to building a radio application where you're actually building RF stuff with GNU Radio and then getting stuff out and using it in your system, that part is maybe not quite so well documented, and very, very few examples out there that I've found that show you how to do that end to end. So yeah, I'll just spend a little bit of time going over some of the stuff I learned, and I think that'll be useful to anyone interested in going down that route. And then I'll talk about how to use it. So the squirrels, just from 10,000 feet, what problem are we trying to solve? If you can imagine an exfiltration box that is inside of a corporate, or not necessarily corporate, but some sort of target site, if you want to abscond with that data wirelessly, there's a lot of standard protocols that might be used. Could just use the existing Wi-Fi network of whatever institution you're dealing with. You may have your own separate sort of Wi-Fi access point. You may use off-the-shelf stuff. Could kind of go down to maybe a Bluetooth option or a LoRa radio, or who knows what. You could roll your own protocol. But kind of one of the key things is somebody, monitoring the RF spectrum. They're kind of going to know where to look, right? They're going to say, hey, is there some suspicious Wi-Fi traffic? Is somebody operating on a frequency that we might expect? And so when I say where, I'm talking about a location in the RF spectrum here. And so the goal of this project was really, what if we could come up with some sort of system that allowed for getting the data out using any frequency we wanted, using any data rate we wanted, any modulation scheme we wanted, any type of baseband encoding that we wanted. And some of those words may not be 100% clear to you, but hopefully you can get the idea that what we're dealing with here in this proposal anyway is the exact opposite of a fixed function off-the-shelf system. This is a system that has very odd and variant behavior from the standpoint of somebody hunting it. And even if they do see a spike on excuse me, on a spectrum analyzer or on some kind of SDR equipment, they aren't necessarily going to be able to make sense of it unless they put a lot of effort into reverse engineering a fundamentally different signal every time they see a spike. So this is kind of from a high level what I wanted to implement. And as has probably been hinted at numerous times already, SDR is a great platform for thinking about systems like this. And so for those of you who aren't that familiar with SDR, software defined radio, and what it is, just at a very high level, you can think of your computer is plugged into some hardware, some programmable radio hardware, and essentially you can code the radio you want. This is a very high level view. There's some caveats to it, but for the most part, you can build the radio you want in code, or at an even higher level, there's a tool called GNU Radio Companion that allows you to kind of graphically build the radio, which is honestly where most people end up, is that graphical level. Throughout the presentation, you'll see how I dived a level deeper into the code level, and you'll see the advantages to doing that. And hopefully I'll demystify that process to where it's not quite so scary to get into that. So just in general, if you want to build an SDR system, you need some kind of computer and you need some kind of SDR hardware, and that's about it. Now, that computer can be all sorts of things. It could be a laptop, could be a desktop, or could be any other small form factor device that supports the SDR software you're looking at. The Raspberry Pi supports almost everything under the sun, and you'll see that we end up using that here in a minute. But on the SDR side, I can talk if anyone has questions after about, choosing the SDR to work with or whatnot. But for this particular project, and you'll see in the demo visually, but I ended up using a couple of different SDRs. And then the antenna is an obligatory thing. You have to plug in an antenna and the SDR. I'll be able to show you that if you haven't actually seen one of these devices up close, but that's no big deal. An antenna is just a few dollars in most cases. And then a power source. In many cases, you might want this Exfil box to be running off a battery, so it doesn't have to be plugged into a wall, and even more conspicuous. And fortunately, things like Raspberry Pis can be run off of all sorts of different battery setups. So let me get into the specifics of what I used, because there are a number of different ways one could have solved this problem. But in my case, well, actually, let me step back and just talk a little bit more about the system. What I did kind of at maybe a 5,000 foot level is I designed a system that has a host that this is going to be sitting outside of the target site in most cases. It could be you sitting in a weird van. It could be a person, or it could be a headless device that's plugged in a few 100 feet outside the target location, but maybe you can control it headlessly. I mean, there's a bunch of different things the host could be, but essentially it's a computer with an SDR hanging off of it. And that computer has some amount of code on it that will transfer to the Exfil box inside the target location a set of RF parameters saying, hey, go ahead and reconfigure yourself to use a particular frequency, a particular type of modulation, a particular type of encoding. Go ahead and reconfigure yourself based on what I'm telling you. That Exfil box is going to receive that transmission. It's going to say, okay, I'm going to change myself to be a different kind of radio. After it does that, it's then going to use that new set of radio parameters and push that information back out to the host. So you've collected some juicy data. You're just kind of sitting on it as this Exfil box, and then eventually the host says, hey, I want it, send it to me this way. And you reconfigure yourself and you send it out that way. The host, of course, knows what that new set of radio configurations are because it just sent them. And so the host is already reconfigured itself and sitting there waiting for the good stuff. And that's kind of at a high level what I built. The one thing that I did do for this demo is I kept the control channel. In other words, this first arrow that pushes out the parameters, I kept that fixed. And that was really just to keep the demo from having more potential risk. And also because this is really a proof of concept design. And if you want to really implement this, it would take a little bit more work in terms of just building in some more error correction and hardening it. And that wasn't something I had the time to do. And so, yeah, I focused on the RF side of this problem, and keeping this control channel fixed meant I didn't have to worry about the host and the Exfil becoming permanently out of sync. So the specific hardware I used, on the host side, just have a standard laptop. Got an Edis B200 Mini, which is an incredible SDR. It's a little bit pricey. It's about $750, I think, but it's, in my view, if you can afford it, if you can justify the cost, it's the best one out there from the vast majority of people. On the Exfil side, I ended up using a Raspberry Pi and a HackRF1, which is a lower cost SDR, not quite as high performing, about half the cost or less. But it also doesn't require USB 3, and you can run the Edis board on USB 2, but you run into some issues, and the same amount of data actually takes more USB bandwidth. I can get into that if anyone's interested, but the HackRF1 is a better match for the current Raspberry Pi setup with its USB 2 ports. And I did a demo of this actually at the Hackenfest 2018, and I used a mobile battery charger pack. So the Exfil box was completely self-contained at that point. But in the demo I'm going to show you today, I actually have that plugged in, and I'm going to apologize for that because the battery pack that I was planning to use, I really thought it was here. And then I talked to my wife, who's in California right now on work, and she told me, oh, sorry, I took that. So my apologies that I can't show you the demo with the battery charger on there, but it really is a very similar thing.
So
And
Paul, a couple of quick
yes,
questions real quick from the
absolutely,
audience.
no
The
problem.
Edis board, the B200 Mini, does that have the ability to send and receive simultaneously?
It does. It is
Okay,
what is
cool.
called a full duplex transceiver. Yes,
And that's one of the advantages over at HackRF1. You can either send or receive. You can't do both simultaneously, correct?
that is correct.
All
Yes,
right.
and that's really helpful for certain types of exploits. If you're doing man in the middle type attacks, and you've got to send out sort of a obfuscating jamming signal, you need to be able to do both at once.
Mhm.
It is possible to plug two hack RFs into a system and have one transmit and one receive. By that point, you've got the cost of a Edis board almost anyway.
Yeah,
The Edis board it has just a much better set of ADCs and DACs on there, which what that means practically is that you just see a lot less noise in your system.
cool. And then another question, quick one from Mark. He said, if you choose not to have the control channel fixed, how do you control that initial communication?
Well,
Predefined configurations based on date, time, other?
you could do it all sorts of different ways, but that's one, and I'll get to this a little bit later, but one of the things that you can even think about this as is a sort of a kind of like a pseudo-random generated frequency hopping sequence where instead of just the frequency hopping, you could actually have multi-dimensional kind of RF parameters where all sorts of things are changing according to a prearranged scheme, and you could sync that up via time, or you could have a kind of a recovery mode, for example, where every so often it looks for a heartbeat, and if it sees a ping at a particular time on a particular frequency, then maybe it resets or something. There's this is kind of gets into the whole issue of wrapping a protocol around kind of the basic RF stuff I have here. There's a lot of different ways you could solve it, and it's more that's kind of a matter of control logic, like figuring out how you want to code that. And that may sound complicated, but hopefully if I've simplified the radio stuff enough, or at least showed you how to simplify it enough, then the problem becomes a lot more tractable. So
Cool.
let me go. This is actually the picture of the system. Got a Raspberry Pi. This is a 3B plus here, and it got a little fancy case. It's got a little fan and a heatsink and everything in it. The hack RF, you can see Lucky 13 back there. You can see this little 900 megahertz stub antenna coming out of it, and there's the battery pack right there. It's actually a fairly large one. That'll run a Raspberry Pi for a while, especially if you want to get clever and start programming the Pi to go to sleep and wake up based on the RTC, the real-time clock interrupts. You could keep this thing running for quite a while. I'm guessing you could probably have it run for more than a day, maybe much more than a day if you were able to kind of work through those power management issues. And that's not. There's examples of that out online. The number of Raspberry Pi examples out there vastly exceeds the GNU Radio examples, I think, by at least an order of magnitude.
Cool.
So on the software side, and when I showed my wife this PowerPoint or this keynote, she immediately pointed out that's a chipmunk, and it is, but just let it go. The software side, I ended up using Ubuntu, and honestly 1816 doesn't matter. I mixed up the systems. I have different laptops, and I've got a ton of laptops and desktops flying around that we're all using different versions of Ubuntu, and the system didn't care. It worked just fine. Using GNU Radio with a bunch of custom Python code on the host side, and on the Exfil side, I ended up using Raspbian. I thought I was going to use Ubuntu Mate, but everything worked cleanly enough with Raspbian that I never bothered. Never really saw a reason to do that. And I've also got GNU Radio installed on the Raspberry Pi, as well as some more custom Python there. So the real key on building the Python code, just like almost any code, is to make sure the design is as modular as possible. And if you haven't done object-oriented programming in Python, it might look a little bit odd at first, or if you haven't done object-oriented programming at all, I would say that it's a lot easier to figure out object-oriented code in Python than it is in C++. And so hopefully hopefully it's not too much of a hurdle. I think the main thing to keep in mind is that classes are just a bunch of code you write, and then objects are variables that take on the type of that class, and that class then has a bunch of data. It's just a kind of a wrapper that has a whole bunch of data and functions in it that allow you to kind of easily make function calls from the very top level that reduce hundreds of lines of code down to a pretty small amount, as we'll see later. I'm not going to walk through the whole code, but I will walk through a few key sections and hopefully give you some confidence that it can actually be done pretty simply once you get some of the grunt work out of the way. But in terms of the Python code, one of the things that I also did that was kind of key is I coded the radios themselves or the radio applications themselves in native Python. I wasn't using the GNU Radio Companion GUI. A lot of times when you think about, let me see if I can, let me just get out of the presentation for a minute. A lot of times when you think about GNU Radio, you think of this, right? You think of this set of blocks that are dropped down into a graphical interface, and you have this nice kind of menu to the right, and you click and drag, and then you connect them all up. If you've played around with GNU Radio, 90+% of the time, it's probably been something like this. And people don't always know, but there's a generate and an execute button. All that generate button does is take this code here and turn it into Python code. And it essentially looks something like this. And so you'll have a block, it'll have a bunch of boilerplate, it'll basically be a class. And then you will, and this happens automatically, you don't even look at it, you don't even see it, but every time you run a GNU Radio flow graph, GNU Radio Companion flow graph, it'll take all of that graphical stuff and just create Python representations of it. And each block will have kind of an instance of itself with the variable, with the parameters that you've set for it. And then they'll all be connected together with this connect function. And then it'll simply just run that Python script. That's really all that's happening when you are doing a GNU Radio Companion design. And so what I did, and there are a couple advantages to doing this, is I kind of dispensed with GNU Radio Companion and coded the blocks directly. And that allowed me to kind of build hierarchical blocks that would sort of swap in different types of radio elements as I needed them. So I could use different types of tuners, different types of modulators, different types of bit synchronizers, and they were all configurable. So I could just kind of swap those in and out during runtime based on the way I built this thing.
Hey, Paul.
And, yes.
Someone just asked, can you share the link to the Python code generator?
So the Python code generator is GNU Radio Companion itself. If you do an install of GNU Radio on your machine, on your Linux box, or I guess you can get it installed on some others.
Already there.
I'd advise against it, but GNU Radio Companion, this interface here, the Python code generator is inside here. And so if I were to say, plop down all these blocks and build this flow graph graphically that you see here, just for example, and then I were to press the generate button here.
Oh, so it's right there.
It's right there. You will get a file in whatever your working directory is called top_block.py. That Python file is going to have all sorts of boilerplate in it, and so some of it's going to be a little bit hard to read because most flow graphs have some graphical stuff going on, and so they'll call the Qt libraries, and so there'll be 50, 60, 70 lines of code involving the Qt stuff. But after you get through that, you're going to see variables like this, and then you're going to see blocks, and everything's got a self in front of it, which means it's part of the object that you're defining, or part of the class you're defining. I won't dive too much into that, but essentially you've got a block definition based on each block that you'll see in here, and then you'll have a connect function call that's going to give, like for this one here, for example, it'll say, connect this particular block's output to this particular block's input. And that's just, there's going to be one of those for each wire you see here.
Kind of like the arrows, right? Yeah, the connectors.
Exactly.
Cool. Thanks.
So, yeah, no, it's a good question because this is, I think, kind of confusing to a lot of folks.
Another couple quick questions. Sorry, Paul, this is CJ. What's the range you get with this setup?
Oh, I've never tried to do anything more than just across a room. So if I made no real attempts to optimize kind of the RF performance of this thing. This is a proof of concept design that just tried to work through the control portions of it and the RF portions of it, and not just the RF design portion of it. But if you wanted to work through that kind of stuff and improve that, there are definitely ways to do that.
Got it. Someone asked about amplifiers as well.
Yeah, if you were working with just these devices natively, you probably wouldn't get much more than, I don't know, 50 to 100 feet. You'd probably want some kind of, if you get this thing near the wall of whatever building you're dealing with, you could probably do it without any kind of external amplifier. But it would probably benefit you to go that next step if you really wanted to get some serious range on it. And a lot of it is not just simply power. A lot of it is going to be kind of what kind of protocol you wrap around it. I mean, you can transmit at much lower power if you have a decent amount of error checking and a decent amount of handshaking. So there's trade-offs between all those things. I mean, obviously you can just blast as loud as you can, and that's one way to solve an RF problem. But
yep. Thanks.
Yeah. So kind of the key point, though, is that I tried to design the radio stack in a way that was, well, kind of like a stack. I mean, the data flows up and down through various kind of levels of abstraction, and also that each level of the stack was configurable insofar as it could be. And this is another thing, this line here about the flow graphs being created and destroyed dynamically. You can read documentation about how to start and stop flow graphs. You can read the documentation about how to destroy them, but that's not typically something people talk about much. What I've found is if you are working through trying to keep a system running in real time, I've had troubles with the HackRF drivers where just some strange error gets spun up and the whole system kind of goes down. I found that if you actually take the time to destroy a flow graph and then restart a new one completely, that you can get around that. So that was kind of one useful thing I found. I'll get into more of the useful tips later. But kind of the key, and this may sound fantastical, but once the radio stack gets built and refined a bit, you can really get to a point where you can create fundamentally new types of radios with just 3 or 4 lines of code. And that may be hard to believe, and you may wonder what kind of caveats I have around that, but I will show you that in a minute. So just kind of from a high level, the Python design or the Python code on the transmit side, it was a matter of kind of coming up with some form of processing the baseband data, which is essentially saying I've got some input data I want to send. Do I need to stretch that out in time? Do I need to manipulate it in some way, add some error checking, what have you? So that's kind of one level of this. Next, that data would get sent to RF modulator. So it would take the information and it would create a untuned RF signal with a on-off keying modulation scheme or an FSK, a frequency shift keying modulation scheme, and it would then take that untuned signal, shift it around so that it goes out at the frequency I want it to go out at, and then send it to an RF sync, which if you're unfamiliar with GNU Radio, that's just the block that connects up to the SDR hardware and then causes the transmission to happen. So that's just something to keep in mind. On the receive side, it's a little bit more complicated. Receive side tends to be more complicated in general. So the transmitter basically is just talking. The receiver has to figure out what's going on. So in general, the receiver is always going to be a little bit harder. And so at the kind of the top level, it's got an RF data source that's, again, this is the GNU Radio's way of interfacing with the SDR hardware. So that means SDR is receiving data and then coming through this portion of the code and then goes into a tuner, which figures out where the signal is that we want to get. And then it goes into, in some cases, an automatic gain control. Because I supported on-off keying, I don't know how much, if anyone has questions about this, I can do a deeper dive, but when you're dealing with frequency based systems, you have to worry about your frequency tuning, but you don't have to worry about your amplitude as much in general. On-off keying systems, you always have to pay some attention to what the amplitude is and make a judgment call about when it's high enough that you're going to interpret it as a 1 and when it's low enough that you're going to interpret it as a 0. And unfortunately, an OOK system, if you just move it further apart, the signal gets weaker. And so the discrimination between the 1s and the 0s starts to get more complicated or more arbitrary. And so the kind of the automatic gain control that I implemented here was just a way to kind of resolve that. And then it just kind of automatically adjusts the magnitude of the signal to kind of get around that issue. And then demodulation, that's just taking the tuned signal that we've got and saying, okay, are these squiggles here a 1 or a 0? And that after that distinction is made, we have to do probably the most complicated part of all this, which is clock synchronization. And that's something that, yeah, that's something that is probably one of the most mysterious parts of GNU Radio, and there are definitely attempts to explain it online, but it's tricky. This is one of the things that I focus on a lot in the second class, the intermediate SDR class I teach, the second one you'll see on the Black Hat schedule. The clock synchronization, it uses it uses a lot of strange software incantations and black magic that I can partially demystify, but it's essentially the difficulty is figuring out when one bit starts and the next bit ends, or rather when one bit ends and the next bit starts. Figuring out that is really kind of the heart of the clock synchronization. And there are blocks that can help with that and implement that. And so that's another layer of the software stack on the receive side. And then once you've got that figured out, there's a little bit of baseband data processing, like figuring out what kind of error checking, whether or not you've got a decent payload or not based on the error checking result. So this is kind of the 1,000-foot view then of the receive software. So one of the real helpful things that I use to build this system is the ZeroMQ framework. If you've played around with GNU Radio, you might have seen the ZMQ or the ZeroMQ blocks in the catalog. They are a really underappreciated tool inside of GNU Radio, and they're not just a GNU Radio thing. They are something that GNU Radio adopted that you can use completely outside of GNU Radio applications if you like. And they're really just a pipe for getting data from one application to another is how I think of it. If you, for example, have data running in if you have a flow graph that's running inside of one of these GNU Radio windows that I showed you earlier, and you just want to get the data out and use it somewhere else, maybe a Python script, maybe another flow graph, who knows. You can actually set up a ZeroMQ socket on one side and set up a socket on the other side, and you can basically just funnel data from one application to the other. This can go from one flow graph to another flow graph. It could go from a Python program to another Python script. It could go from a flow graph to a Python script. That's the beautiful thing, is there's really no significant constraints on that. It's also, you can go from one machine to another because you're using a TCP/IP layer or TCP layer to go for data transport. So this was useful for me in testing. It was useful for debugging. It was useful for getting payloads out of transmitter flow graphs or into transmitter flow graphs and out of receiver flow graphs, which honestly is probably the least understood and least well demonstrated part of learning how to use GNU Radio. So kind of got ahead of myself talking to this slide because I already mentioned that, yeah, you can use any kind of combination, flow graph to flow graph or flow graph to code. And the messaging, that's another kind of aspect that's interesting. If you played around with GNU Radio at all, you might have noticed that there are message type connections where you're not just sending a stream of constant data, but you're actually sending an asynchronous message. So every so often you just say, hey, I've got some information, do this thing. And you can send that in the form of a message. And that can happen at any time based on external control code. You can generate this message, and this ZeroMQ framework allows you to deal with both constant streams of data as well as the asynchronous messages, which is what makes it so incredibly useful. So now let's go ahead and see if the demo works. I'm going to go ahead and do two things. First, I'm going to show you physically what I've got going on. Just to keep it all on camera, I've got the, excuse me, get a shot of this not vodka here. So the Exfil box is this portion of the system right here, and when I get it done, I'll show you a little bit closer. I don't want to break it down right now and drag it over, but this is essentially just the Raspberry Pi in the same case I showed you earlier in that photo. This is the HackRF1 with the 900 megahertz stub antenna. I'm just kind of sticking around in the ISM band here, which allows unlicensed use for low power and low duty cycle signals. And so this is going to have some data on it. This over here is going to be the SDR that's connected to a machine that you can't see, but it's just a computer, just a Linux box. And this is going to play the part of the host. And so the host here is going to say, give me some data and give it to me in this particular way. And then the Exfil box is going to say, okay, going to reconfigure itself to send the data back the way the host has asked for it. And then the host is going to receive that. So both sides are going to be acting as transmitters and receivers. They're all half duplex. There is a way to build a full duplex version of this if we could get a full duplex SDR over here. But because of the way I've designed the system, it's just a half duplex system. Transmit, receive, everybody switch over, transmit, receive. So now that I have shown you that, let me go ahead and bring up my terminal windows. So I'm just SSHing into, this window is SSHing into the host or the Linux side, and this window is SSHing into the Raspberry Pi. So this would be happening autonomously in a real scenario, but just to kind of show you what's going on both sides, I've kind of got both windows up. So let's see, I'm going to bring up the host, and all that's going on here is S is just the software platform. So this thing will, I have a test mode, but you can use it with the EDIS boards, the UHD boards, or the HackRF. So all I'm doing is starting up the host side radio using the EDIS configuration. And then I'm going to start up the Exfil side on the Raspberry Pi using the HackRF. And so there's some kind of driver stuff that gets done. I would have loved to suppress this to give a cleaner, prettier output, but it is almost impossible to suppress this input or this screen, this terminal output. So at this point, the Exfil box is just running autonomously. You're just getting to see what it's doing. And then on this side, I've got the host. So everybody's SDR has been turned on. It's just waiting right now. I've got a default setup and somebody asked about that earlier, like how do you know at the beginning how to transmit and receive, what parameters to use? And both the host and the Exfil box has a default setup, which in this case is going to be a 912.5 megahertz transmit frequency. Yeah.
So Paul, we had a quick question. They said, is that initial signal from the host some standard one? Meaning, would someone be able to intercept and read the configuration?
Well, they'd have to reverse engineer the configuration. There's nothing standard about this. I rolled this on my own. So they could definitely, we'll actually see the raw bytes from this in just a second. So yeah, they'll see some raw bytes, but they won't necessarily have any way to determine what those raw bytes mean.
Yep. And that's configurable, right? I mean, you can change that whatever you want it to be. Yeah.
Oh yeah.
This helps for like demonstration purposes, proof of concept as well. Yep.
Yes, definitely. So you can see all these different parameters. These are all things that are being sent in raw binary form to the Exfil side that then basically they can be configurable in one way or another. So if I choose not to really do anything, but just say, hey, just leave everything at default, I can hit the C button here, and what happens is the EDIS board goes through a kind of startup loop. Oh, that's nice. And then, well, let me go ahead and try this again. Awesome. Try it. How many times do you have to try it? Well, I am getting some overflow issues. Let me try one thing. All right. Sometimes you just have to unplug it. This would be a problem in the real scenario, I give you that. It's a pretty uncommon situation, though. I really haven't run into that much at all. So
we're gonna slaughter our chicken here before we try it again.
Yeah, exactly. Let's see what the entrails say this time.
Roll the bones.
So you can see here, and we saw this previously as well, but then it seemed to have run into something.
So Paul, while you're kind of working through that, I'm going to work through some questions real quick, if you don't mind.
Well, actually, believe it or not, as much as that caused a lot of problems, it actually got a signal through. And this is kind of a testament to what I was saying earlier about how the HackerF drivers can get a little wonky sometimes, but if you kill the entire flow graph, destroy the flow graph object, and then restart it up, you can get yourself out of bad situations. And so what actually happened here is, see how it says payloads received? I basically took the Poe poem, the Raven, and I just kind of stuck it on the Exfil box, and I said, give me a couple words every time you ping me, right? And so what happened here is 1,000,000,001 overflows, but there we go. Before all that overflow garbage, what happened is we started up, we received a bunch of garbage commands because my idea of error correction is a simple arithmetic checksum and sending the transmission like 20 times. It's not clean, it's not elegant, but like I said, this is a proof of concept type of situation. And so I, excuse me, eventually after a few malformed transmissions, I got a valid command string here. And this is just a decimal form of the raw data, excuse me, of the raw data that was sent from the host over to the Exfil box. And that said to the Exfil box, okay, use these parameters, which are just the defaults. And then it switches around and it transmits the information back, and we're able to get this single line payload. So I haven't done anything really except simple transmission at this point. So what I can do is use this kind of clumsy engineer coded interface to change the frequency now. And so if I start off at 912.5 megahertz, let me just change it to 913.6. And you can see how that changes up here. And so now this is the frequency I'm dealing with. And let's get crazy and change the modulation scheme. Right now it's 1. And I'm just going to make it FSK instead of OOK. So now I've changed both the frequency and the modulation scheme. If I wanted to, I could change the preamble. And this interface has only kind of built in these 3 things. All of these are variable under the hood. I just haven't built the kind of the GUI, well, not even GUI. I haven't built the kind of the command line chooser stuff to change the rest of these, but it's easy enough to do. If I then press C for kind of send configuration, let's see what happens. Okay.
Oh,
so this time,
through.
Maybe something's coming through. Command too short. Receive command. Raw payload. So it looks like it didn't go through that time. Awesome. I'm going to give it one more try. If you want, you can ask or if you had a question you wanted me to get to, and this will keep running kind of until it times out, and it's like, well, no payload received. Let me try it again, and I'm not quite sure what happened there, but I'm going to try it again.
It's the power adapter. It's always the power adapter. Your wife took it. It's the wrong power adapter.
I'm going to blame that. It's that. Well, if you do have some questions, I know you said go ahead. I can multitask and deal with this issue while you are asking me the questions if you have any.
So one of the questions was, if we're a blue team and we actually want to start scanning our space, what are some things that we can do? And I think GNU Radio has some really cool utilities where you can kind of see a waterfall flow graph of the different frequencies and what is being transmitted. Do you have any other ideas on what people can do to actually identify possible wireless signals that should be of concern?
Yeah, it's tough, but definitely you can roll your own tools or just use simple flow graphs in GNU Radio, like you were saying, and that it takes 2 blocks strung together to create a simple kind of spectrum analyzer, a very simple one. The kind of the difficulty you sometimes run into is stuff may not be transmitting all the time, and so intermittent transmissions create fun complications, and so you need something more like a kind of like a logger that says, hey, an interesting thing happened here at this time at this frequency. And so that requires maybe a little bit more effort, either coding or there's some interesting tools out there. There's the GR, what is it, inspection, I think, which is a module that you can add on to GNU Radio that allows you to do some signal detection as well as kind of some signal identification. I haven't gotten to use it a bunch, but I will talk a little bit later about a cool platform that that someone we know is going to be presenting later this year that kind of wraps together a bunch of cool SDR tools into one place. So
cool. Now, I do want to throw out for everybody, since the demo kind of went down and he's restarting it, we will tack on at the end of this video a working version of the demo, because I'm willing to bet, once again, the power adapter or just simply rebooting everything will bring it back up. So it will actually be there. So if that's okay with you, Paul, we just record it offline and then just tack it in. And the cool thing about doing that is all the people that watch the recording will be like, yeah, that just looked like it worked flawlessly. And we can completely fix this in post.
You did see it.
Well, and and I thought we actually had a video of you doing it at Wild West Hack and Fest as well.
You know, I think the Gremlins got it.
The Gremlins got a hold of it. Of course, the Gremlins got a hold of it. That's just what Gremlins do, right?
That's true.
Very true. So I've got a couple more questions.
I will show you this, and we'll get it cleaner later. But I did just change the frequency. and the modulation scheme in this particular instance. We got a couple of bad commands, but eventually, 2 of them got through, and that happens.
Okay.
And you can see that the frequency was changed from 912 to 913.5. The modulation scheme was changed from 1 to 3. 1 represented OOK, 3 represented standard FSK. And you can see we got a payload through.
Oh,
so
nice. So
I think the gremlins kind of temporarily got it.
Personally, I think it's too close to the printer. I think the printer was actually interfering. It's generating all kinds of weird frequencies.
I expect HP was at fault. Yeah.
Yeah, let's blame HP. That can't go bad. So some other people were talking about, this whole entire thing is a great proof of concept to demonstrate risk from like air gap networks, right?
Yes.
If somebody has a highly secure network, you can set up a box very easily. And this could also be transferred over to anything. Like people were talking about some Raspberry Pis and the ability to actually transmit over certain frequencies just with the Raspberry Pi itself. And and this is just, once again, this is just proof of concept demo showing data going from one side to the other over an air gap network, correct?
That is correct.
Awesome.
Definitely proof of concept. And I think it's the real attempt was to try to demystify how to build a GNU radio application, because I think that's a huge barrier for a lot of folks. And I think if they realized and just believed in themselves that they could actually code these things, I think that a lot more people would be taking advantage of them.
Cool. And then do you have the flow graph for what you set up for transmission and received shared out with everybody?
It's in GitHub, but
and we did share out your GitHub repository link.
I definitely will. I'll share that.
Mike, share that out. Cool. Yeah. So we can share that so people can run it. Do you have?
And just a note though, I mean, because I coded most of this stuff in Python directly, I think there are a couple of GRC files in there that were used for test and for kind of proving out a few concepts that I left in the GRC directory, but that's not how this thing runs anymore. This is fundamentally a code-based application now. So if you remember what I showed you earlier about the blocks being instanced manually in Python code, that's what you're seeing run here.
Yep. And we have people that are like, no, leave the errors before we finally got it working in the recording. We will leave that all in the recording. Absolutely. People are like, with SDR, a lot of times it's black magic. It works and people don't see all the like going back and forth, gremlins, changing frequencies, and then all of a sudden getting it to work. Once again, kind of a strange field that not a lot of people are in right now at all.
Hey, John, another quick question.
Yeah, go ahead.
People want to know, is there any place where there's a schedule of Paul's training?
I actually shared the links out. If you go into the chat window, I shared out the links to Wild West Hackin' Fest, and I also shared out his Black Hat class as well.
Awesome.
And then Paul, I don't know if you had any more training coming up as well.
Well, so I do training in a couple different ways. If an organization wants me to come, I can do training specifically for an organization. I have 2. And I don't have dates for them yet. I have 2 planned trainings, one in the Seattle area, one in the DC area, where I'm just, open training, show up, enjoy. The information about that is going to be on my website. I hate to give you another website, but it's factorialabs.com. And you can find all the kind of the details about what my training is. I try to give you like a step-by-step, here's the stuff we're going to go through over the 2 days of each class. And so you can kind of get a real good and kind of insight into what I'm actually going to show you.
Yep. And setting this up, you had 2 Ubuntu systems, right? The Raspberry Pi system was transmitting, and then another Raspberry Pi was receiving. Is that correct? And they weren't Ubuntu in that situation.
No, it was a Ubuntu Intel PC was the host, and then that was sending the initial stuff, and then the Raspberry Pi was the receiver.
Got it.
For the initial, and then it flipped around and became the transmitter, and it started transmitting the poetry to the host again.
Okay, very cool. And I see we do have Once Upon a Midnight Dreary While I Pondered, so we can see it's going through there. Now, another question, as part of this, we like to send out the slides and kind of a thank you for attending email. Is it possible you could do a breakdown of like shopping lists, like what equipment you actually had so people could reassemble it at home?
Oh, yeah, sure. Right. Yeah, I'd be happy to. Yeah, I could get that out in any number of ways, whatever's good.
Cool. Now, Paul had a question. He said, building a frequency hopping scanner has the same problems as detecting Wi-Fi in different channels, except scaled up. SDRs have a limited range they can look at depending on the device, and limited bandwidth, once again, depending on the device, as well as different frequencies. So how would you go about trying to deal with something that is actually doing frequency hopping when you're reverse engineering, to be able to reverse engineer that, to be able to pull it out of the air and then look at it?
So there's a couple different challenges on frequency hopping. The first is finding it, and finding it can be tough if it's intermittent as well, because it's an intermittent transmitter is its own problem because you've got to find it in time, and then frequency hopping gives you a second dimension that you have to worry about. And so if you have an idea of where it might be, that's obviously either because you found it or because you suspect a particular type of hardware might be in play. Then it's a matter of setting an SDR to a bandwidth wide enough, a sample rate large enough to capture enough spectrum that you can see all of the hops inside of that.
And I think that also gets into Martin's question. Martin asked a question. He goes, well, can't you just load this data into Splunk? And that makes it really hard because you're looking at the overall bandwidth and the amount of data that you're pulling in. And I think that you'd run into some issues if you were just doing sampling. I really don't see how loading SDR data into Splunk would be a viable option for actually plumbing that data, do you? Because it's just a lot of data.
Well, yeah, I mean, so an SDR, using a GNU radio interface anyway, there are ways to kind of pare this down a little bit, but just as a back of the envelope calculation, you're generating a complex sample every time with your SDR. And so if you're sampling at, say, 1 megahertz, just simply at 1 megahertz, that means you're generating 1 million complex samples every second, and each complex sample is 2 4-byte floating point numbers. So you're generating 8 megabytes per second just to look at 1 megahertz of spectrum. And so if you want to look at 10 or 20, which is maybe pretty common when you're trying to seek out a signal, at 20, you're talking about 160 megabytes per second. And so the amount of, I mean, video takes a lot. Oftentimes you think of video as being the thing that consumes the most data, but IQ files are crazy.
Yep. And then to close it out, I think Dallas has the best quote. He goes, well, great job. Now I'm going to go hide in my Faraday cage. So good to know. Well, let's go ahead and close it out. Thank you very much. Oh, yeah. Do you have something else for us?
Well, I did want to quickly go through a few things, but
okay,
I know it's gotten late, so I don't want to, and I've talked about a lot of this stuff, so I'm not going to go through the slides at speed, and I can just be done at any time you need. But I did want to get to a few things. I showed a lot of this stuff already, the stuff I learned. Just kind of the big takeaway though, and I promised I wouldn't step through code. I'm only going to do this one thing here. Here, for example, is given the stack that I built, I have a 65-line radio file, most of which is a bunch of imports and argument parsing and command line argument junk. And then when you look at the actual radio stuff, I just have some classes, some objects that take some default parameters. I modify the parameter based on what kind of modulation scheme I want to use. I create an object for the type of radio I want to build, just using those parameters. I switch it to receive mode, and then just debug statement there. And I just have a while loop, and it just receives data. I mean, that's the entirety of the radio, and then I have a shutdown. So, I mean, the goal really, when you're building these radio stacks, in my view, is to try to come up with something that's abstracted enough that at the top level, you can really focus on the control aspect of it. What do you really want the radio to do at any given time, and not have to get into all of the minutia about the frequencies and how you're modulating and whatnot. So that's kind of the key, and that's hopefully what I want to impress people with, is that this stuff can be distilled into a very clean and usable type of solution. And then the last thing I wanted to mention, because I wanted to give a plug, some possible improvements. I think I've mentioned all of these already. How you get it, that was one question. MyGitHub.com, or my GitHub is Paul G. Clark, and I have this particular thing under Exfil, EXFIL. Yeah, you can take a look through the code there. Like I say, it's engineer code, and a few things I would have done differently, but it works. And there's actually there's a real hack on the receive side somewhere, but it works. You can ping me if you want to know why some strange piece of code was written some way. And this is
toys.
The one thing I did want to kind of get out there is Josh Conway is somebody who's going to be speaking at Circle CityCon in Indianapolis later this year about this really cool project he's been working on, where he has 3D printed a case, and you can get the files for that on his GitHub, and he has basically plunked a RTL SDR onto a Raspberry Pi 3B Plus, and got a cool keyboard and LCD monitor, and he's basically got a little RF hacking machine that you can go around. It's got Universal Radio Hacker and Spectrum, mouse jack, multi-mon for flex pagers and stuff like that. And he's even managed to get a little bit of crude transmission going without any SDR hardware whatsoever, just by toggling a GPIO pin.
That's so cool.
It is. It's noisy, but it is just hacktastic. It's great that he was able to get all that working. And so, yeah, you can, if you're in Indianapolis, you should definitely check out his presentation. But you can also just see he's got a GitLab account.
And
this
isn't inexpensive enough that this is a great project if you have like teenagers and you want to get them into SDR stuff. This would just be a fun project to actually stand up and do.
Oh yeah. I mean, you could definitely, find signals. You could mess. Wow. You could.
I don't.
I'm not going to give any advice about what you can or can't do, but you could do some interesting signal intelligence stuff.
Come out to Waldo's Hacking Fest. Go in the middle of the woods and do things that would normally be illegal. Without context, that entire statement sounds very wrong. But you all know what I mean, right?
Hey,
all right.
Is there really any law out there? I don't know.
No. All right. So thank you very much, and appreciate it. Hey, I think that we should do another one. Let's talk about creating some of my favorite ones are just creating a little FM radio or a little FM pirate radio station where you could play audio files back, and that might get some people into trouble. But I think that might be a great next webcast if you'd be willing to come back. How to set up a little FM radio and then do your own little FM station to really piss off the FCC.
I would be more than happy to come back.
Cool.
So yeah, definitely thanks for the chance to come on.
You bet. Thank you so much.
That cat wants a stretch, or just wants some screen time. I didn't realize your cat was such a diva. That's impressive.